All right, so we'll continue with exercise 4C. So next we'll go on to question number 8. So we are going to continue sums with horizontal circular motion. Okay. All right. So a hemispherical ball of radius 15 centimeters is resting in a fixed position with its rim horizontal. Okay. So the particle of mass simple m is moving at 14 radians per second, that's omega, in a horizontal circle around the smooth inside surface of the ball. Okay. So inside the ball you have a particle which is going in circular motion. Find the distance d of the plane of the circle below the plane of the rim of the ball. Okay, so basically the particle is going in a is moving in circular motion inside the rim of, I mean inside the hemisphere. So basically you have to find how far below the center of the plane of the circle is the plane of the rim of the ball. Okay, so the first thing is here, let's draw the diagram. Okay, so let's see what exactly they are talking about. Okay, so you have a hemisphere, and then you have an object of mass m which moves in a circular path, and then this is the center of the circle. So this is the basically the when they say find the distance d of the plane of the circle. So this is the plane of the circle. Distance d of the plane of the circle below the plane of the rim of the ball. So sorry, the plane of the circle is this because this is the circle that the object is moving, right? So this is the circle that they are talking. So when they say plane of the circle, this is the plane of the circle. Are you guys with me? This is the plane of the circle, and then they are asking the plane of the rim of the ball. So this is the rim of the ball. Can you see? So plane of the rim of the ball is this one. So basically distance D is the distance between these two circles. Okay, so this distance between them. This is what they meant by D. Okay, so they're asking you to find this distance. All right. Okay, so how do we find this distance? Uh, okay, so let's mark all the information you're supposed to find the D value. The radius is given to you as 15 centimeters, right? So radius of the hemisphere. Okay, so basically, before marking that, let's draw a force diagram. Force diagram is extremely important, and I have told you when it comes to horizontal circular motion, there are two things to do. One, you always consider vertical equilibrium whenever an object is performing horizontal circular motion. It's always in vertical equilibrium, and the other one is you always apply F equal ma towards the center. So, what are the forces acting here? A ball of mass m means weight is mg. The weight is mg, and the normal reaction. The normal reaction, as I told you previously, the normal reaction is acting perpendicular to the surface, and this surface is a part of the hemisphere. So when you act perpendicular to the surface of the hemisphere, the normal reaction must pass through the center of the hemisphere. Okay, so do you recall this rule? The normal reaction must pass through the center. The line of action of the normal reaction should pass through the center of the hemisphere. All right, so then let's mark this. So I'll mark this angle as theta. All right. Okay, so you're supposed to find the distance d of the ball. So anyway, to do this, there are only two things to do, right? You consider vertical equilibrium, and you apply F equal ma towards the center. All right, so let's get started. Okay, how does this work? The next thing is okay. So let's apply. Let's go for vertical equilibrium. Okay, so considering vertical equilibrium, guys, what do you see? I think you can see mg is acting vertically down, so you can resolve r upwards. So when you resolve, you get r sine theta according to the way I marked theta over here. So this is capital R sine theta. Capital R sine theta should be equal to mg, right? So this is the first equation. The next one, we will apply F equal ma towards the center. When you have circular motion, always you should apply F equal ma towards the center of the circular motion. So when I apply F equal ma towards the center, I think you can see mg is vertical. That has nothing to do with the horizontal circular motion. The only one who acts towards the center of the circle is this one, right? R cos theta. Can you see? So the next equation, the force that acts towards the center is R cos theta. Okay, so component, force component equals mass into acceleration. So acceleration, when it comes to centripetal acceleration, you can use R omega square or V square over R. Okay, so since omega is given here, I'll go with R omega square. Okay, so R here is the radius of our circular part. Okay, remember that. Not the 15, because 15 centimeter radius is the radius of the large hemisphere. Okay, but our circle is below the level of the hemisphere. So this circle doesn't have a radius of 15, right? The large hemisphere only has a radius of 15. So this R is actually at this point unknown. So capital R cos theta equals mr omega is 14 radian per second. So 14 square. Okay. All right. So after we come to this point, I think the best thing we could do here is let's actually divide the two equations. Okay. So by dividing, we can actually get rid of the r, isn't it? So r sine theta over r cos theta equals mg divided by mr 14 square. So you can see several of the most of the variables cancel out. So r goes away, m goes out. So these were unknowns, right? So they cancel out. Sine theta over cos theta gives you tan theta. G over r times 14 square. And now guys, it's time to input the tan theta value. So if you look at tan theta, so look at this right angle triangle. If you look at this, do you see the right angle triangle over here? So if you look at the right angle triangle over here, this is a 90 degree. So the considering tan theta here. Guys. So tan theta from this triangle, opposite over adjacent. Opposite is D, adjacent is R. Can you guys see that? Okay, so I think we did not get to use the radius 15 centimeter at all. Okay, so if I had gone to use the sine cos values individually, this length would have been 15 centimeters, or in other words, 0.15 meters. So actually, I didn't go to use this radius, the radius of the hemisphere. Okay, so basically, what I need to do here is tan theta is d over r, opposite over adjacent, right? This simple. All right, so using d over r. G over R into 14 square. So you can see the R will cancel out, right? The R will cancel out and you can get D equals G over 14 square, and we can simplify and get the answer. So D equals 0. I think you get an exact answer, right? G is 9.8. 14 square 196. So D equals 0.05 meters. This comes exactly. So leave it as it is. Make sure the answer is, this is actually an answer that's in meters. Okay. So which means you could even say the answer as 5 centimeters. So basically the particle is moving in a circular plane 5 centimeters below the rim of the hemisphere. Okay. So I hope this is clear with everyone. Okay, so now let's move on to question number 10. Okay, so a particle P is moving in a horizontal circle with center C and radius R with a radius R. P is in contact with the rough inside surface of a hollow right circular cone. Can you see? So you have a cone, and basically the particle is inside the cone. So basically now our main shape is a cone. All right, so they say the cone is fixed with its axis of symmetry vertical and its vertex be pointing downward. The radius at the top of the cone is 6 meters. Okay, so at the top, the radius is 6 meters, and the cone has a perpendicular height of 2 meters. When r equals 0.1, the maximum constant angular speed at which the particle can move without slipping from its path is 14 root 5 radians per second. Guys, can you see this word without slipping? So basically, and this is where we, I think you can, and you can also see the word they used here. What? There is a rough, right? You can see the word rough. Okay, and without slipping. So basically, this definitely gives you the idea that there is friction. Okay, so you need to mark a proper force diagram here. Okay, they're asking you to find the maximum angular speed without slipping for r equals 0.3. Okay, so this is a different radius. Okay, so for r equals 0.3, what's the maximum angular speed you can achieve? All right, so first thing is let's draw a clear diagram and mark all our forces. The force diagram is critical. Okay, so guys, now over here, first thing is we need to draw the force diagram of the particle. So you can see I have drawn a slightly larger version of this diagram over here. The thing is, you can see now, basically they are keeping this particle not in one place, right? So they first they say when r equals 0.1 meter. So basically when the particle is moving in a radius of 0.1, they have given you something and they are asking you gain a speed when it's at a radius 0.3. So guys, over here, when you're marking the force diagram, okay, first thing is to mark the force diagram. One thing you should clearly understand is that when it comes to the normal reaction, okay. Now, in the previous questions, we dealt with hemisphere. So in a hemisphere where you have the circular surface, the normal reaction, when you make a perpendicular to the circular surface, it passes through the center of the hemisphere. But this is not a circular surface. So you see, this is not a circular surface. Okay, so therefore the normal reaction that you make, the 90-degree plus when when you are in different positions, obviously when the particle is in different positions, there is no such thing called that it should pass through the center. Okay, maybe it passes through the center at a very specific point, but since the particle they have shown like several places that the particle is in the normal reaction, there is no necessity for the normal reaction to particularly pass through the center. All right, so normal reaction is just making a 90-degree with the surface. So it does not necessarily need to pass through the center because it could you could in another place the normal reaction just goes like this. All right, so that's important. That phenomenon occurs only and only in a hemisphere. Okay, so in the hemisphere, regardless where the object is in, regardless how far below or far above the plane, regardless of the place, always a normal reaction would pass through the center because it's a circular surface. Okay. All right. So coming over here, you can mark the normal reaction. So let's mark the other components. We have the weight. So the weight is, they have not given us the mass, so we'll mark it as empty. Okay, so the particle performs a circular motion. Okay, and this is the center of the circular motion. So they are saying this is the center of the circular motion. All right. Okay, so now let's start working on the calculations. Okay, so guys, other than the normal reaction and the weight, the other thing you need to consider here is the friction, because they say we have a friction here. So basically, you need to consider now how to mark the friction, to which direction. Now they are saying, they're talking about the maximum angular speed, right? So basically the particle is moving around in this circular path, and when it achieves the maximum speed it could possibly achieve for this particular radius. Okay, so what's the tendency? If you're moving at a higher speed, at the highest possible speed for this particular radius, the tendency, now think about this, you need to visualize this. Is the particle having a tendency to try to move upwards outside the circle or try to move downwards? I hope you guys can see, children. Now, if the speed, let's talk about the other side. What if it slows down? Like if this particle slows down, you can understand the tendency is to go down, right? Because you're slowing down. Slowing down means you try to come down because it's too slow. But if you're going really fast, if the particle goes really fast, the tendency is that it will try to move up. Isn't it slow? If you're going really slow, you will try to go down. But if you're moving really fast, the tendency is the particle will try to move upwards. So therefore, the friction The friction, if you are moving at the maximum possible angular speed, the friction will be acting downward. So this is one of the most key and important things. So the maximum friction, so basically the particle is about to slip, right? So they're saying the particle can move without slipping from its path. Basically your friction is acting downward. Okay, so this is really important. Friction is acting downwards means the particle is tending or trying to move upwards. And therefore, when the particle is trying to move upwards, it means the particle has it is moving at the maximum possible speed. Okay, so that's really important. Okay, but if they, sometimes they do use the word minimum speed. So if they use the word minimum speed, it means the smallest possible speed to keep it on this circular path. So the smallest speed means the tendency is that because the speed is lower, the tendency is to move up. In that case, the friction would be acting upwards. In that case, the friction would act upwards. Okay, so the direction of friction is really important here because the direction of friction is what tells you whether the particle is moving at the maximum speed or the minimum speed. Okay. All right. So this is the maximum speed, and let's say that's omega. All right. So what you need to do now here is let's go for the let's go for the vertical equilibrium. All right. So to do this, let's mark an angle theta here. So let's resolve. So upwards you have r sine theta. So guys, let's try to get this angle. So this is a 90 degree. All right. So this is 90 minus theta. Okay, and then this is again gonna be theta. I hope you guys can see how the geometry here, right? Can you? Okay, so if this is a theta, the small angle is gonna be 90 minus theta. So this is again gonna be theta. Okay, so this is theta, and this is theta. Okay, so the geometry here is really important because you need to resolve. There are two forces you need to resolve here: normal reaction and the friction. Okay, so if you consider vertical equilibrium at this point, so vertical equilibrium will be, so let's mark it. So upwards you have r sine theta, r sine theta. And you can see guys, now the thing is when you're resolving, it's not only the normal reaction that resolves, but friction also resolves. So friction, you can see you have a component acting downwards, right? There's a friction component acting downwards. Can you see? This side you have a friction cos theta. And I hope you guys can see. So towards the center, we have a friction sine theta. Can you see when you resolve the friction, you have towards the angle f cos theta, and away from the towards the center of the circular motion, you have f sine theta. Can you see? All right. So what I need now, what I need here is for vertical equilibrium. So r sine theta acts upwards, mg and f cos theta acts downward. Mg and f cos theta acts downwards. Agreed? All right. So this is my first equation. Okay, so this is my first equation. So considering vertical equilibrium, let's apply F equal ma towards center. So when we apply F equal ma towards center, this time towards the center, what are the forces acting towards the center? All right. So then when you apply F equal ma towards the center, so you can see this time towards the center of the circle, you have two forces, right? It's not just the friction sine theta, but you can also see that the normal reaction. The normal reaction also gives a component. So r cos theta towards the center, right? Can you see? So towards the center, normal reaction gives a vertical component and also a horizontal component. So the horizontal component of normal reaction is also part of the centripetal force. So now in this situation, you can see centripetal force consists of two forces. Okay, so what are the two forces? R cos theta and F sine theta. r cos theta plus f sin theta. Those are the two centripetal forces equals mr omega square. Okay, so mr omega square. So these are the two equations. Can you see? All right, so they are giving you two scenarios here. When r is 0.1 meter, the maximum speed is 14 root 5. So when r is basically r means the radius of the circular path. Okay, so when r is 0.1, the maximum speed is 14 root 5, and they are asking you to find omega when r is 0.3. All right, so okay, so let's see how do we find this? How do we solve this? Okay, so guys, the simplification here is going to be like kind of like really long, but there is a really short, there is a shortcut that you could use here. So the longer way, like let me just show you, kind of like direct you like how you would normally like try to do this. So what you would do here is first, I mean, you could try to solve the equation simultaneously, maybe try to get the R and F value. And when it comes to the theta, okay, there is actually a way to find this theta. So let me just show you on that. The way to get the theta, guys, if you can see here, I hope you guys understood that this is theta, this is 90 minus theta, this angle, and this again becomes theta, right? Through geometry. And also if you see through alternate angles, guys, can you see through alternate angles? This is again theta, the angle at the, the cone. Okay, so at the vertex of the cone, so this is a theta. So guys, if this is theta, you can see that both of them are the same angle over here. The axis of the cone is dividing this exactly into two, right? So you can see, you can get the theta value here easily because you have the large right angle. So basically, you can get the ratio, right? So sine theta ratio can easily be found. Sine is opposite over adjacent, so 6/2. Okay, opposite over hypotenuse. Okay, so opposite is 6/2, which is basically 3/1. So cos theta and theta can be found in this manner. Okay, but this is just one way of doing the sum. Okay, so you could use the sine cost ratios over here. Go ahead, solve simultaneously and get the R and F values. But that's not what I'm gonna do here. Okay, that's not what I'm gonna do here. So I'm gonna do this in a short way. So what's the short way that I'm doing? So guys, you can see here they are telling us when the radius of the circle is of this particular circle is 0.1, the maximum speed is 14 root 5. Okay, they are asking us to find the maximum value of omega when the radius is 0.3. So when the radius is 0.3, what's the omega? That's all they are asking you. Guys, if you see this, okay, so when radius is 0.3 means, now over here, if the radius is 0.1 and when the radius is 0.3, I think you can see the particle has moved a little bit upwards, right? Because radius has increased. But even though the particle is moving upwards, say the particle is in the new position is over here with radius 0.3, I hope you guys can see that that does not change the force diagram, right? The force is the way they act, the mg acting upwards, the normal reaction acting to the perpendicular to the surface, the friction acting downwards. So all of these forces will kind of be repeated over here. Okay, are you guys getting what I'm saying here? All right, and the next thing over here, why am I saying that these values don't change? Because obviously you can see now the maximum friction is mu r, right? So mu is a constant, and over here normal reaction also, you can see that the weight of the particle stays the same. So basically, you have the same force diagram repeated for the particle, which is at a slightly higher elevation. Okay, I hope you guys can see that. So basically what's happening here is because, I mean, maximum friction is a constant. That value doesn't change unless the surface changes, right? So basically these F cos theta values, F sin theta and the normal reaction, they are not changing. So if they're not changing, you have the particle, they are in two elevations. One, the particle over here with radius 0.1 and again the particle over here with radius 0.3. Okay, but at the radius 0.3 position, the force diagram is exactly the same. Vertical equilibrium and horizontal equilibrium towards the center, the force diagram will exactly be the same. So I hope you guys can see what I'm doing over here. So M radius at the bottom point, radius is 0.1 omega. Omega is 14 root 5 square, right? So this is the, this is the R cos theta plus F sin theta when you're at this level. So this is going to be the same Again, the r cos theta plus f sin theta will again exactly be the same value when you're over in the higher elevation also. Exactly the same, because the r cos theta plus f sin theta value does not change. Even this ratio doesn't change, even though you are in two different elevations. Okay, so again, so that's why I'm just directly equating. So r cos theta plus f sin theta at the higher elevation is also m, radius is 0.3, and we need to find the omega square. We need to find the angular speed, right? All right, so the m can cancel out, and you can get your omega square by using 0.1 into 14 square into root 5 square is 5 over 0.3. So it's just a matter of typing this in the cal and getting the value of omega. So this is the easy way of doing. Okay, but there is another way of doing. The other way of doing is where you actually solve for r, where you actually solve for f. Solve this equation simultaneously, get those values, and again apply it over into this equation for the new value of r. Okay, but even though at the two different elevations, the force diagram is exactly the same and none of them change. Okay, because we are at the maximum friction, mu r friction is going to be the same. Even though you are at a different position, the mu r doesn't change, right? Normal reaction doesn't change. So basically, all of these things are remaining the same. So mr omega square value is constant at r cos theta plus f sin theta at the maximum friction. So therefore, all you have to do is to equate the mr omega square value at the two different places, at the two different radiuses, and you can get the omega value at the radius 0.3 respectively. Okay, so omega is going to be the root of this entire thing. So root of the entire thing will be 14 root 15 over 3. Guys, this is something you should, type in the cal and get it. So basically, you could give the answer here in exact form because we are not using anywhere an approximation, or we do not use any where we use T as 9.8. So there are no approximations here. Therefore, you could leave the answer here in exact form, or like in the exam, they would be very specific if they want exact or not. Or else you could keep it to 3SF and say you kept it to 3SF. So that's 18.1 radians per second correct to 3SF. All right, so any of them are fine. So in this case, even the exact answer is okay because you're not doing any approximations anyway. Okay. All right, so we'll move on to question number 12. They say a car travels around a bend of radius 300 meter on a road which is banked at an angle of 10 degree to the horizontal. So guys, can you see you have a car traveling at a bend. So it's a bend road, and not only a bend road. The road is also banked, which means the road is kind of slant. I mean, the road, so if you draw the road, this is the road, like how the road makes an angle. So basically your road goes like this. Can you see? The road is kind of banked. Okay. A car travels around the bend of radius 300 meters on a road which is banked at an angle of 10 degree to the horizontal. This is 10 degrees. The car is assumed to be moving at a constant speed in a horizontal circle, and there is no tendency to slip, given that there is no sideways friction. Okay, so there is absolutely no friction here acting on the car. Find the speed of the car. Okay, so let's draw the diagram. So basically here, actually the kind of like the cone diagram should work. Okay, so you could draw like this. Okay, the cone diagram actually works. So for the car, you can draw a particle. Okay, so this angle is 10 degrees. Okay, so this is the radius. Okay, so mark all the forces now. They say there is clearly there is no friction at all. If there's no friction, what you'll be having here is you'll be having the normal reaction and you'll be having the weight. Okay, so normal reaction, and you have the weight of the car, which is mg. Right, so these are the forces that you have, and this is 10 degrees. Okay, so this is yeah, so alternate angle you have 10 degrees. So again, this is quite easy. All you got to do here is what, go with the two equations. Basically you apply You go for vertical equilibrium and then you apply F equal ma towards the center. That's it. And you can easily get the answer. Okay, so guys, we are this force diagram is done. So now let's move on to the calculation. So remember, there are only two things to do: vertical equilibrium and F equal ma towards the center. Okay, so this is 10 degree. This is gonna be 90 minus 10, 80. Again, this will be 10 degrees. Okay, so I'll work with the 10 degree. All right, so first I'll go for the vertical equilibrium. So considering vertical equilibrium, what have we got considering vertical equilibrium? We have R cos t, R cos 10, right? R cos 10 will be equal to mg. Agreed? R cos 10 will be equal to mg. And when you apply F equal ma towards center, when you apply F equal ma towards center, you have towards the center, I think you can see it's R sine theta, right? So R sine theta, R sine 10 theta, this is the force that's acting towards the center. So R sine 10, R sine 10 equals m R omega square. So basically they're asking us to find the constant speed. Okay, so in that case, we'll use V square over R. V square over R, radius is 300. Let me put the value of R sine 10 equals m V square over 300. Let me move the 300 to the other side. So 300 times R sine 10 equals mv square. The second equation. So I think it's easy for us to find the v value here. Best thing, the easiest thing to do here is to divide. So I think I'll divide the second equation by the first, or you could do 1 divided by 2. I'm doing 2 by 1 because it's I can make v the subject easily then. 300 R sine 10 divided by R cos 10 equals mv square divided by mg. So guys, you can see most of the variables cut out. R cuts out, m cuts out. So you have here 300 sine 10 over cos 10 is tan 10. The g comes as a multiplication times g equals v square. So v equals 300 g tan 10 and whole thing root. So now definitely when you use G as 9.8, you can give the answer correct to 2SF or 3SF. Okay, so over here, you give your answer to either 2SF or 3SF. Yeah, so this is going to be 22.8 meters per second. Okay, so you can get the answer from the class. Okay. All right, so we'll move on to question number 14. A bend in the road is modeled as a horizontal circular arc of radius r. The surface of the bend is banged at an angle alpha to the horizontal, and the sideways friction between the tires and the road is modeled as being negligible. So guys, if you can see, this is basically the same story as previously, right? I mean, you can see the only difference is now instead of working with figures, you're actually working with signs. You don't have figures here, you're working with letters. Okay, so they're saying again the sideways friction is between the tires and road is negligible. When a vehicle is driven around the bend, there is no tendency to slip. Show that according to this model, the speed of the vehicle is given by root RG tan alpha. So guys, basically it's the same diagram as we did before. So you have a banked road. Okay. So the road is banked at an angle alpha to the horizontal. It's basically the same diagram that we drew before. Okay, and so you have a particle and you have a vehicle. Okay, so you have a vehicle, you can just draw it like, okay, and it's going to go in a circular path around the bend road. Okay, So this is going in a circular path around this road. Bend in the road is banked. Okay, as a horizontal circular arc of radius r. So here the radius is r. Okay, so let's mark the forces. So you have the normal reaction. Normal reaction acting perpendicular to the surface of the road. And you have the weight mg. Right, so that's it. Basically, this question is quite similar to what we did previously. Just the fact that you are working with figures. We are working with letters. So this angle here is alpha by alternate angles. All right, so again, it's the same story as before. So this alpha, this is 90 minus alpha, which means this is again the alpha. All you have to do again is apply vertical equilibrium and F equal ma towards the center. So let's go for vertical equilibrium. So when we apply vertical equilibrium, we get here R cos alpha, right? R cos alpha is acting upwards is equal to mg. R cos alpha is equal to mg. So this is our first equation. Then next, let's apply F equal ma towards center. When you apply F equal ma towards the center of the circle, so you can see the center you have here R sine alpha. R sine alpha is the angle that's acting towards the center, right? So R sine alpha, that's it. There's no other force, is equal to M. And since we're supposed to find the speed of the vehicle, we'll use mv square over R. Okay, so radius of this circular path is R. That was given to us. The radius of the path is R. So basically simple R into capital R sine alpha. Capital R is normal reaction. Equal mv square. This is equation number 2. So you can easily get the answer by dividing. So 2 divided by 1, second equation. So you get simple R, capital R sine alpha over capital R cos alpha equals to mv square, equation number 2 divided by equation number 1, divided by mg. Can you guys see? So capital R cancels, m cancels. And you have here simple R sine alpha over cos alpha, right? Sorry, this is not theta, this is cos alpha, right? Yeah. Sine alpha over cos alpha is tan alpha equals v square over g. So take the g to the other side. So you get here r g tan alpha equals v square, and therefore v equals to the square root of rg tan alpha. And this is the show that. Can you guys see? Show that according to the model, the speed of the vehicle is root rg tan alpha. Okay, so in part B, they say suggest with reasons which modeling assumption is likely to give rise to the greatest inaccuracy in this calculation. So we have done some modeling assumptions here, right? So they've told you to neglect a certain thing, so the vehicle is moving. You have air resistance, and what else? Yeah, we also neglected the sideways friction, right? So basically, the biggest assumption and the modeling assumption that we've done here is, I think you can understand when a vehicle moves on the road, definitely we need to consider the friction, right? So model assumes there is no, the biggest inaccuracy here is when we assume that there is no friction, okay? Okay. All right, so next I'll move on to question number 18. They say a bend in a race track is banked at 30 degrees. A car will follow a horizontal circular path of radius 70 meters round the bend. So again, it's the same story. Okay, we are having a banked road, a car is traveling. So I'm just drawing the car as a particle. And they say now the coefficient of friction between the car tires and the track surface is 0.4. Okay, they have given you the coefficient of friction. Find the maximum and minimum speeds at which the car can be driven around the bend without slipping. Okay, so without slipping, what's the maximum and minimum? They want both the speeds. So guys, this is really important. Okay, so let's draw the vehicle. Okay, so this is the vehicle. I'll draw it as particle. Okay, so this is just drawing it as a particle. Okay, so this is the vehicle, and you have the okay, and you have the weight. So weight of the vehicle is mg, and you have the normal reaction. So you have the normal reaction. Okay, so the angle with the horizontal is 30 degrees. Okay, okay. So a car will, this car is going in a horizontal circle. Okay, so the car is traveling in a horizontal circle and radius is 70 meters. Okay, so radius is 70 meters. The radius of the circular path. All right. So they're saying here the coefficient of friction between the car tires and the track surface. Basically, now the car is moving on the road, but we are talking about the sideways friction. Okay, so we are talking about the sideways friction, whether it's moving, its tendency to slip up or to slip down. That's what we are concerned here when it comes to circular motion. Okay, so not the frontward motion, but basically it's the circular motion, the maximum speed and minimum speed. I think I did tell this a while ago. Maximum speed, minimum speed makes a difference. Okay, so basically I told you if you are trying to go at the highest possible speed in this particular radius, the particle has a tendency to slip upwards. But if you are going at the minimum speed, at the lowest possible speed, the tendency is that this particle will try to slip downwards. Okay, so that's what they're saying, find the maximum and minimum speed. So basically, if you're trying to, I'll first go with the maximum. Okay, so if you're going with the maximum speed, so let me a copy of this. All right, so if we go with the maximum speed, okay, the friction will be acting. Remember, if you're going at the maximum speed, the particle has a tendency to slip out. It will try to move outside. I mean, it will try to go out. Okay, not inside. So basically, if you're trying to move outside, friction is opposing the direction you're trying to move. So friction opposing that, friction will act downwards. Okay, guys, friction will act downwards. Okay, and basically, because you're about to slip, you have the mu r friction, the maximum friction. Okay, so you have the maximum friction here. The maximum friction. All right. So now it's the same story again. We'll mark the angle. So this is 30 degrees. By alternate angles, this is 30, and this will again become 30 degrees. All right. So moving on. Okay, so let's go for vertical equilibrium. So we have R cos 30, right? R cos 30 acting upwards. R cos 30 acting upwards. Mg is acting downwards. And guys, you can see mu R. Mu R cos 30 is to the horizontal. Mu R sin 30. Mu R sin 30 is acting downwards. Can you see, guys? R cos 30 is acting upwards. Mu R sin 30 is acting downwards. Let me take them to one side. R cos 30 minus mu R sin 30. equals mg. This can be our first equation, considering vertical equilibrium. And the next one, you can consider horizontal equilibrium. So when you consider not horizontal equilibrium, what do we consider? F equal ma towards the center. F equal ma towards center. So when you apply F equal ma towards center, I think you can see you have normal reaction sine 30, right? So r cos 30 is acting upwards, r sine 30 is towards the center, plus mu r cos 30. Normal reaction sine 30 plus mu r cos 30 equals, we are trying to find the speed. So we are going to find the maximum speed, right? So equals m v square over r. So radius is 70. Let me move the 7 to the other side. So I get here 70 times r sine 30 plus mu times r cos 30 equals m times v square, the second equation. So I think obviously you can see what I'm trying to do here. I'll be dividing. So equation 2 divided by equation 1. So 70 r, I think you can see that we can take a r, okay, let me write it first. 70 r sine 30 plus mu r cos 30 divided by r cos 30 minus mu r sine 30 equals mv square over mg. Guys, can you see? Second equation we divide by first. So r is common. I think you can see up and down. You have you can take a r out. You can factorize the r out and cut it out. Can you see? You can take factorize r out and then cut it. Okay. So basically, not just cutting individually r to r here. That's not what's happening, right? So you take r, factorizing r out, and from the numerator and from the denominator, and r cancels out. Okay. M cancels out. So I think we can get the answer easily, right? 70 sine 30. So this is something you can give in the calc. 70 sine 30 plus mu value was given, isn't it? Mu value was given in the question. Mu is the coefficient of friction is 0.4. Can you see? Coefficient of friction is 0.4. So plus 0.4 cos 30 cos 30 minus mu is 0.4 sine 30 equal v square over g. So I'll bring g up. G is up over here. So I just brought the g numerator up over here. So it's a matter of typing everything in the calc and you can get the answer and then root and get the answer. So let's do that. Guys, I think I made a slight error here, right? When I took the 70 to the other side, the 70 just not only multiplies with r sine 30, but also multiplies with mu r cos 30, right? This 70 over here should come as a multiplication of the whole side, isn't it? Maybe adding a bracket like this would help. The 70 over here. I hope you guys can see what I'm talking about, right? The 70 which I brought up should multiply the whole r sine 30 plus mu r cos 30. Okay. So let's keep the 70 out. It's 70 times sine 30 plus 0.4 cos 30 multiplied by g divided by cos 30 minus 0.4 sine 30. Okay, and then you root this. Okay, so I hope that part is okay, that you guys saw the error. Okay. So use the root of this whole thing. G. You can bring the G in front if you require. G is 9.8 times sine 30 plus 0.4 cos 30. cos 30 minus 0.4 sine 30. Okay, so just give the whole thing in the cal and you'll get the answer. So you definitely give it to 3SF when you use G as 9.8. So the answer is correct to 3SF, 29.5 meters per second. Is that correct? Yeah. 29.5. So basically it's something you can give in the cal. Okay, so you can do that part. That's 29.5 meters per second and this is the maximum speed. All right, so that's the maximum speed. So now we'll go to, they're asking us to find the maximum and minimum. Okay, so now let's go to find the minimum. So the next thing is to find the minimum speed. I think you can see to find the minimum speed, as I told you, it's just the tendency, the direction of the movement of the object. So if the speed is low, the particle has a tendency to come down, to slip down. Therefore, it's just the direction of friction that's changing. So friction will be directed upward because the particle is now having a tendency to move down. So your mu r friction, friction is acting upwards. Agreed? All right, so 30 degrees comes over here. So all you got to do is to, again, do the same thing. Consider vertical equilibrium and consider F equal ma towards the center. So vertical equilibrium, so when you consider vertical equilibrium, okay, I think you can see that this 30 degree comes over here as well, right? The 30 degree comes here as well. You can see either by vertically opposite angles or you have corresponding angles. So basically 30 degree comes here. All right, so now we can resolve. So upward you have r sine 30. R sine 30. Sorry. This is not r sine 30, right? So the 30 degree comes here as well. So this is going to be r cos 30. R cos 30 plus mu r sine 30. Guys, can you see? R cos 30 and mu r sine 30 away from me. Equals to mg. So this is the first equation. R cos 30 mu r sine 30 is equal to mg. And then when we use F equal ma towards the center, okay, so when we use F equal ma towards center, we have the centripetal force. Guys, you can see. So R sine 30 is acting towards the center. Can you see, guys? R sine 30 is acting towards the center. But mu r, you can see it's mu r cos 30. Guys, can you see? Mu r cos 30 is also acting to the horizontal direction, but it is acting away from the center. Right? Mu r cos 30 is also in the horizontal direction, but it's acting away from the center. So that's going to be minus mu r cos 30. Minus mu r cos 30 equals to mv square over r, right? Radius is 70. Taking the 7 to the other side, let's not do the same mistake as previous. 70 times r sine 30. I use the bracket now, okay? Minus mu r cos 30 equal mv square. Second equation, and we can divide. So equation 2, you can divide by the first equation. So 70 times r sine r sine 30 minus mu r cos 30 divide by r cos 30 plus mu r sine 30 is equal to mv square. Equation 2 divided by equation 1 is mg. So m cancels out, and over here, as I told you, you can factorize an r outside from the numerator, and you can factorize an r outside from the denominator, which means the r will cancel out because r is a common term for everyone, numerator and denominator. So basically, you would get here 70. I'll take the g to the other side. 70 g times 73 times sine 30 minus mu is 0.4 cos 30, right? Maximum, minimum, mu value doesn't change. Mu depends on the surface. Cos 30 plus mu is 0.4 sine 30. Equals to v square. V equals 73 sine 30 minus 0.4 cos 30 divided by cos 30 plus 0.4 sine 30. Guys, can you see? So you get the answer. Take this answer and this should give you the smallest, the minimum value of the speed. So correct 3 SF. G is 9.8. So you can give G value as 9.8. 70 times 9.8. And then multiply with this. So it's 9.94 meters per second. Okay, correct to 3 years. Basically, that's correct to 3 years. All of this. And this answer is correct to 3 years. Okay, so you can see this is the maximum speed and the minimum speed. So the minimum speed. And this was the maximum. So guys, the maximum speed and minimum speed depends only on one thing, and that depends only on what? The direction of the friction. Okay, so remember, direction of friction acting downwards, the object has a tendency to move up. That happens if the object is moving at its maximum possible speed. And the other one, the object, the minimum speed is when the object has tendency to come down the bank surface. Basically, it's because it's losing speed. Therefore, the speed is low. So basically, at the minimum possible speed, your friction is opposing the movement where the object is trying to go down. So friction is acting upward. Okay, so this is basically basically sometimes in the exam they could ask you to find the range of possible values of the velocity, the speed range. What are the range of possible values for the velocity in order to go in this particular radius? So then the range of speed could be anywhere in between these two. So as long as your speeds are in between is greater than or equal the minimum and less than or equal maximum, you can maintain that particular speed level, that particular level of the circular motion. Okay, so if you increase the speed, you will definitely go up. If you are decreasing the speed less than, if the speed falls below this, you will move down. Okay, so I hope you understood this part clearly. Also, okay, so we'll move on to question number 20. A particle of mass m is attached to one end of a light inextensible string of length L. The other end of the string is attached to a point vertically above the vertex in a smooth of a smooth cone. Okay, vertically above the vertex of a smooth cone. So this is a smooth cone. Okay, so this is your particle and this is the inextensible string. The semi-vertical angle of the cone is theta. Okay, so semi-vertical angle over here, this is theta. And the string makes an angle, makes a constant angle of theta degree with the horizontal. So this is also theta. Where theta is bit less than 90 and greater than 45, pi over 4, greater than pi over 4, less than pi over 2. Given that the particle moves in a horizontal horizontal circle with angular speed omega, show that the tension in the string is given by this equation. Okay, so basically the particle is moving. Now it's moving on the surface of the cone. Guys, can you see it's moving outside the surface, not inside, because the cone is inverted and you have a particle. The particle is hanging from the ceiling and it's moving outside on the surface of the cone. It's going in a circular motion. Can you see? Okay, so it's basically you have to do the same thing again, even though this looks, this has so much of expressions here. It's everything is done in terms of letters. And you have only two things to do. Apply F equal MA towards the center and apply vertical equilibrium. So that's it. So let's do that quickly. All right, so let's mark all the forces acting on this. I have taken a larger diagram here to make it easier for us. So basically the particle is on the surface of the cone. You have normal reaction. And then you have the weight, particle of mass m, so weight is mg. Okay, so it's moving in this circular path. Okay. And then they're saying, okay, and we have the tension. Yeah, so we have the tension in the string, right? So this is the tension. So guys, you need to mark all the forces. So I think first thing we can see here is this angle theta. You can get uh, alternate angles here, right? So alternate angles here, and this is the theta. Can you guys see? That's the first thing you can mark. So this is theta. All right. So because we need to apply vertical equilibrium and equal m towards the center. So we need the angle. Okay, and then what about, so we can now easily resolve tension. So tension cos theta towards the center, tension sin theta upwards. But also I need an angle for R, because I need to know an angle either over here or here in order to resolve R. Okay, so how do we get the angle corresponding to R? All right, and then how about the angle for R? So what I'll be doing for that is I'll be using this angle. If I use this theta, I mean, theta is the same in both the places, but to get this angle over here, this theta, you can see through corresponding angles, I can get theta over here. This is completely geometry. Okay, corresponding angles. These two guys are corresponding. So if this is theta, this is 90 minus theta, isn't it? Because this is a perpendicular. And since again, these two guys are perpendicular, 90 minus 90 by 2, this is again going to be a theta. Guys, can you understand the geometry here? That's really important. This is theta, this is 90 minus theta. And since these two are also perpendicular, this is ending up becoming theta again. Okay, so that's what needs to be done here. So this is theta, 90 minus theta, and this is the theta that I require. All right, so everyone is ready now. It's time to apply vertical equilibrium and F equal ma towards the center. So applying vertical equilibrium. So applying vertical equilibrium, we have T sine theta acting upwards, right? T sine theta acting upwards plus R, sorry, yeah, T sine theta plus R sine theta. So both of them are sine ratio away from the angle. T sine theta plus R sine theta is equal to mg. This is the first equation. And the next one, we will apply F equal ma towards center. So towards the center, I think you can see we have tension cos theta acting towards the center. Guys, can you see? T cos theta acts towards the center. And you can see here R cos theta is acting away from the center. Can you see? They are both horizontal. So T cos theta acts towards the center minus R cos theta. They are both horizontal, but T cos theta acts towards the center of the circular motion. R cos theta acts away. That's why it should be minus. Equals mv square over r. We are supposed to find, yeah, our answer is supposed to be in terms of omega. So we'll use mr omega square. mr omega square. Okay, so we are supposed to make, show that the tension, we are supposed to make T the subject. Okay, so how do we make T the subject? Okay, so you can see we show that m is a term that's already there, omega should be there. So I think you can see we don't have a R. There's no R. I mean, this particular, I mean, R here represents the radius of this circular motion, but there's no R. They have used in terms of L. So guys, if you can see here, the radius, guys, can you see here, the radius, this radius is equal to, I think you can see it's L cos theta. Guys, can you see? This is the length L and this is the angle theta. So towards the angle, L cos theta is equal to R. Okay, resolving. So R is equal to L cos theta. So we can use that also. Cos theta minus R cos theta M L cos theta times omega square. Okay, so this gives us, this makes things a lot easier for us now, right? Why? because cos theta is common to everyone, because there are three terms in this equation. T cos theta is one, R cos theta is another, ML cos theta omega square is another, and everyone has cos theta as a common term which we can remove. Cos theta can be factorized and removed. Okay, so that gives me an equation T minus R equals ML omega square, and that gives me a substitution for R. So I can write here T minus ML omega square is equal to R. Guys, can you see? I took that minus R here. T minus ML omega square is equal to R. Okay, so this is a easy substitution. Now let's put the equation 1. Substitute to 1. So T sine theta plus R sine theta equals mg. So T sine theta, R is T minus ML omega square, right? So R sine theta. Guys, can you see? I replace the R here. Okay, equals mg. And now all we got to do is make T the subject. So T sine theta, T again T into sine theta is T sine theta minus ML omega square sine theta equals mg. Right? So T sine theta plus T sine theta is 2T sine theta. Take these terms to the other side. Mg is here plus ML omega square sine theta. Right? Guys, do you agree? ML omega square. All right. So time to make T the subject. So T equals 1 over, I think you can see the 2 sine theta. I mean, it goes down as a division. Mg plus ML omega square sine theta divided by 2 sine theta. Guys, can you see? So just keep an eye on the show that. So in the show that you can see they have taken the half and m out. Sine theta is not out. Okay, so half and m. So basically half is from here, right? This is the person who contributes the half. And these two you can take out as common and take the m out. So half m, and you have here t plus L omega square sine theta divided by sine theta. Guys, can you see? So t equal half m. Separate the sign, the g over sine theta plus L omega square sine theta over sine theta. So sine theta cancels out. T equals half m. G over sine theta, guys, you know 1 over sine is cosec. So g cosec theta. Can you see? G cosec theta plus L omega square. And I believe this is your shoulder, right? L omega square plus G cosec theta. Yeah. L omega square L plus G cosec theta into half m. So we have the same thing basically. Can you see? Can you see? So we have got the shoulder. So this is the shoulder. Okay, so basically you need to be able to simplify something like this and just manipulate the equation a little bit in order to get the shoulder. So I hope horizontal circular motion is now clear with everyone. Okay, so just two simple theories. You have to master the force diagram and you have to just apply vertical equilibrium and its equal ma towards the center. Okay.